As a part of your daily activities, you are mounted with this question as to whether the product design that you are developing is going to meet the warranty issues or not. This presentation is intended to help the design engineers to come up with reliable techniques and methodologies to adopt in order for them to overcome the warranty issues or to understand the mean time between failures as a part of the design process. The agenda of this presentation is we look at the current challenges facing the industry, we look at the overview of the design process, whether we should look at warranty or factor of safety, how to develop reliable designs, and what are the benefits of this approach. Where do we stand today? Typically, the design department is always faced with the challenge whether the design is going to succeed or not. We develop a design, we send it for prototyping, we get the parts, we assemble them together, we should do a dimensional verification before we assemble them and put them together and ensure that the quality issues are met before we test them. Once we have tested it, the physical prototype, if it breaks, we have a component or an assembly which has broken and we do not have any clue as to why it has happened so. Subsequently, we do a lot of different testing before we perfect the design for those test conditions, and then we release it into the marketplace. Typically, in any organization, we are mindful of the quality of the product only until such time the product leaves the gate of our office. If we look at the definition of the word quality as given by Junichi Taguchi, he says, quality is the financial loss to society after the article has been shipped. In other words, it is necessary for us to look at the qualitative aspects of our design and the processes that we adopt to achieve the quality upfront within the factory shop floor, and also it is incumbent upon us to maintain that quality after the product leaves our premises and gets into the hands of the customers. It is in the second part of the phase of the product that we encounter product recalls, lack of performance, so on and so forth, which necessitates that our service engineers visit the company and address these issues post-production, post-supply and delivery, sometimes even when your invoicing is happening and you have not been paid yet. So in other words, if we are able to address these quality issues upfront, what we are going to face with the end customers during the life of the product that we have guaranteed to them, we stand to succeed in terms of profitability, in terms of customer satisfaction, and in terms of repeat business for our products. When I say our products, our customers' products that go into the marketplace time in and time out, time again. So the rework due to the performance issues eats into the profitability of the company. So if you look at the finance department funding all the qualitative problems subsequently down the line after the product has been shipped, we know where we stand. So let us look at it from a design process per se. If quality is the paramount importance, why are we not looking at it as the initial objective in design? So if you take the initial objective in design and you say qualitatively, these are the fit, form and functional requirements that we need to address, and we can classify them as internal to the organization and external after the product has left. The internal to the organization is what you call as the assembly objectives, the design for the assembly and the GD&T drawings, so on and so forth, the design for manufacture and other things. But when you look at the two circles down there, you will see that the design for life and design for performance are two paramount things that we need to look at when this product is shipped and it is going to be facing qualitative issues subsequently down the line at the marketplace or at the customer place. A problem of the customer solved at the design stage, after the problem that is going to be faced by the customer after the product has been shipped, is something that we save money in the company, as a result of which we save money for ourselves and grief for the customer. This presentation, we are going to be focusing on the design for life and design for performance as a part of our initiative in the technological process that we deliver to our customers, in understanding the warranty issues and how to get away from factor of safety calculations towards design for life. Now, validating the design for life increases the confidence in the design that it is going to perform throughout the warranty period that we have self-professedly declared to our customers. It improves our reliability on our product. Now, when we talk about reliability, we talk about two things. One is the qualitative reliability and the quantitative reliability. In this presentation, we are looking at ways and means to address the quantitative reliability. Software helps us to develop the reliability models on the qualitative side. We already have it. But is there a correlation between what we see in warranty terms and costs and recalls from the customer with regard to the quantitative reliability that we need to have? It's few and far between. So this design validation process, as a result of the way we are doing it, it eliminates the errors that comes in as a result of our design calculations. It reduces the input cost into our material. Just put enough material to cover your warranty costs. I repeat, just put enough material to cover the warranty costs. Then what about after warranty? If we are saying that the warranty for our product is 2 years, and we are going to have trouble-free performance for 5 years. Ladies and gentlemen, we are away from what the market is seeking. You have transacted a business with your customer, ensuring a 2 years warranty. If you look at necessarily, I know this is going to be a little different from your conventional presentations in terms of design for reliability. If the customer comes into a warranty issue after the warranty period, it could be as a result of abuse of your product. We are designing fail-proof designs, fault-proof designs, reliable designs, not abuse-proof designs. If we come back and say that we want to ensure that in spite of abusing our product should live, the product may live, but our company may not. So the difference between abuse-proof design and fail-safe design is we protect the failure of the product during the warranty period. Go and look at your washing machines in your house. They give you a warranty. After the warranty period, you pay for it. The more you pay for it, the lesser the pleasure in the user experience. So you may not go back to the same customer, to the same product manufacturer for a repeat business. You are a customer lost if the cost of your investment is not going to give you a return over a period of time, let us say beyond warranty over the next 3 years. If it is a maintenance cost which is affordable, customers come back to you for your products over and over again. But if your product is going to fail during the warranty, it is grief for you. So you are assuring a superior performance during warranty period. The 1960s and the 70s, the 1960s and the 70s are the period in which we saw people talk about warranty and migrating towards away from factor of safety. A lot of times we have seen man went to the moon. Man went to the moon on the basis of a reliable design. Man went to the moon on the basis of a design which cannot fail, because failure was really not an option. But today, if we extend the same process for a product to be produced on the earth, the company suffers as a result of the product's higher warranty costs or because of higher costs of ownership for you at the expense of your customer. So if the product cost is important at the initial sales side and the increased profitability is a must, an enhanced warranty is a threat, and improved reliability is mandatory, then you move away from factor of safety towards warranty. The warranty-based designs is typically what we look at from the point of view of design for life. The weakest link in a chain is not the strongest link. It is the one which fails first. The chain was only as strong as the weakest link. If we are able to protect the weakest link, we have a reliable design in our hand. Let us say we look at machine design. We ask these questions: will my shaft break? What is the life expectancy of the system? Can I meet the weight target? Will my power consumption be more? If my power consumption is more, it's going to lead to a stress on the electronics and the electrical drives, leading to a failure over there, probably during your warranty period. Would anything be breaking under the warranty period? Now you ask the question, for the warranty that you want, what is the cost you want to incur? So the sales department in your organization, let us say they have 3 different products from the same configurable product with 3 different warranties. One for 1 year, this is the cost. One for 2 years, this is the cost. One for 5 years, this is the cost. The advantage of providing this to your sales department is they have options to present in front of the customer, and the customer makes a choice and an informed decision what he is getting as a result of what is there on the table. You are going to buy a new car. When you buy a new car, companies claim a warranty of 20,000 kilometers or 2 years, 30,000 kilometers or 2 years, 50,000 kilometers or 2 years, but then they put a caveat, whichever is earlier. Why? That is because it is designed for life. If we are able to accept it and add on to it the additional warranty that we are willing to pay upfront to the car as a result of what you are seeking, the peace of mind, that's exactly what your marketing and sales department need to have in terms of informed decisions for your customers, in terms of the reliability of your product. So the machine design validation, as you should see here, if you are looking at a cost reduction and factor of safety do not go hand in hand. You say a factor of safety, you want a factor of safety of 2. I ask the next question, how is it tied to warranty? Next you say, I want a factor of safety of 2.5. Now between 2 and 2.5, the cost of your product is going up exponentially. Do you have a tie-up between the Goodman diagram that you use for your factor of safety towards the life calculation? No, you do not. So what do? We go about looking at the fatigue life characteristics of the product. More to that in the later part of the presentation. Let's look at the next example. The powertrain validation. It could be a gearbox. It could be a transmission in a vehicle. It could be any one of these things which is converting the energy from one form to the other. It could be an electrical device. When we are looking at all these things, are we developing near net shape design? I was giving a set of lectures to an audience on design, and I asked this question to them: which country do you think is superior in terms of design? And 9 out of 10 participants said it's Germany. I asked this question, why is it not India? There was a stoic silence there. One of the members pointed out that is because if according to our design calculations, if the shaft size is 65, our engineers will, after taking into consideration the factor of safety, pad up on top of it and give it as the next standard shaft of 70 millimeters, and they will never touch the 65. The Germans would take 65 millimeters as the LMC condition and would build up the tolerances unilaterally on the other side because they are confident on their designs as compared to us. This was a statement made by one of the design engineers, a designer, an owner of a company who had more than 35 years of experience in design. So if you look at this presentation, the last but one statement comes over there and says, what is the abusive load that the system can handle? I want to bring home the point that there are three different loading conditions for which a designer tries to protect his design. One is called as the operating load. The second one is called as limit load. The third one is called as design load. If the customer starts to use the product that you have given at the design load, his warranty is invalid. He needs to pay you for what he is doing. What he is doing is bordering on abuse. So what you have to give to the customer is, for operating load, a certain mean time between failure. You put that on your service manual explicitly and in your warranty conditions which the customer signs across and accepts. Then you give the limit load on the model, on the product that you have designed. You do not give the design load. The moment you give the design load, I have seen companies, they mistake it as operating loads and they operate upon that, and the supplier pays through his nose in terms of warranty costs during the warranty period that he has provided to the customer. Now let us look at vibrations. There are situations where you design against vibrations. There are situations where you design for vibrations. The second one is more interesting than the first. First, let me delve on the first one, where we try and isolate the vibrations. The most intrinsic part of an anti-vibration solution to any customer is a mount design. The product may perform, but if the mount is not able to withstand the energy and it transfers the energy over to the product is bound to fail on account of the mount. So this case, every one of the mount that you see on, let us say, a vehicle, it is designed for a particular life. You would see, if you are owning a car, you will see that after 3 to 4 years, they will replace your engine mount. After 3 to 4 years, they would replace your subframe mount. After 3 to 4 years, they will say your suspension mounts have to be replaced. That is because the life has been used up. If you say I spent 2,000 rupees subsequently after 4 years to replace the mount, that is okay. But if you replace the mount 3 times during the warranty of the product, that is your money taken from your customer, which is being stolen away from you either because of your design or because of abuse. Now let us look at the second case where vibration is necessary. There are situations where you need to bring about surface finishes on components either as a part of the process because it is being used in food industry or because it is being used in medical industry, where the burnishing and the other operations that you do in manufacturing, the post-manufacturing residues that are sitting on the component when it is being assembled, you go through a cleaning system. The cleaning system sometimes involves a vibrator. In those cases, the vibration devices have to work in particular frequencies. You are introducing a vibration necessitated for the product acceptance, but it has to meet the life. So there are two different ways in which we can look at life. One is called as high cycle fatigue. The other one is called as low cycle fatigue. A lot of times, 9 out of 10 times, we look at the high cycle fatigue. Anything above 3 to 5,000 cycles of load testing can be classified as high cycle fatigue. Anything between 3,000 and 5,000 or less will be classified as low cycle fatigue. Why is it high cycle and why is it low cycle? The high cycle is in the elastic zone. The low cycle is in the elastoplastic zone. So in other words, if you are doing an accelerated durability testing on your lab and you are saying 5,000 cycles of this is equivalent to 3 years of warranty, then you know where you are. The trick is to establish the reliability model between this number of cycles versus the warranty that you have provided. This is exactly where these kinds of simulation tools and technologies help you to bridge that gap. It is not that you are going to avoid a physical testing after you have done a design validation. No and never. It is just that you are going to reduce the number of testing. You're going to do it once and you're going to get it established and you're going to sign off. When you are signing off, you are reliable, design is going to work and you have the confidence it's going to achieve that. This is exactly where simulation-based or design-based validation for life is important. Equipment design. A lot of things people are talking about is the American Society of Mechanical Engineers, Section 8, Division 2. If you look at the Section 8, Division 2, the stress calculations is moving away from closed form equation-based calculation towards the appendix which talks about the finite element validation. A lot of times, if you have chosen a flange thickness, if you have chosen a nozzle design, if you have chosen a pressure vessel thickness, either for vacuum or for internal pressure, you are going to be, for a pulsating load for example, you are going to be deciding for certain cyclical stresses that are coming as a result of the operating load that you are trying to address in eliminating as a failure mode during your warranty calculations. Necessarily when we have 3 different designs for 3 different warranty with 3 different materials and 3 different costs, the choice of winning the order with the customer making an informed decision is higher, more so in rotating equipments, scrubbers, dryers, centrifuges, operating gate valves, so many different things where these kinds of validation becomes important with design for life. System validation. System design validation is an absolutely important thing. Gone are those days when a customer says, "Sir, I have delivered the pump. The pump worked good on my test bed. But the pump has vibrations when you have put it inside on your factory shop floor." We have a case wherein one of our customers is having 4 units of a centrifugal pump delivering for the entire petrochemical plant. Now the pump is delivering for the performance. The pump vibrations on the test bed are no issues. The pump delivered everything before the accepting engineer signed off at the supplier's place. It was shipped across. After a year it was commissioned along with the other things because it's a petrochemical plant. And lo and behold, the pumps have vibrations which are at unacceptable levels at the bearing locations. Now, if the supplier comes in and says, "I have given you based on warranty calculations that it is working in my shop floor, in my test bed, and if it is a problem at your end, it is your problem," he is not going to get a repeat order from that customer. When we investigated this problem using simulation, we looked at the cavitation, we looked at the blade bypass frequency, and we said it is because of the clearance between the impeller and the housing leading to a cavitation loss and leading to a loss upfront and downstream because of the pipe bends. A combination of this was pushing the critical speeds towards the operating speed, leading to vibrations. Whose problem is it? It is a joint effort which has to be taken by the pump supplier along with the petrochemical industry major. Now, we cannot absolve ourselves of the responsibility of a system-based validation, whether it is a static equipment, or it is a transportation device, or it is a farm equipment, or it is a gearbox, or it is a general heavy engineering machinery. At the end of the day, the bottom of the iceberg, the money that we spend, the time we spend with the customers post shipment of our product, as Junichi Taguchi said, eats into our profitability. Similarly, we look at the machine tool design validation. Again, life is an important thing. The yield is important. The CP/CPK is important. The deflections are important. The estimated forces are important. We are always looking at design for life as compared to factor of safety designs. Material handling equipment. In this particular case, the material handling equipment was to be serving for a period of 5 years. The warranty was 5 years. This is a very classic case where the entire scissor platform was 3.2 tons. The payload it was supposed to take was 1.6 tons. We reduced it. Our customer, using the simulations, reduced it from 3.2 tons to 1.9 tons. It is a savings of 1.3 tons. Now the next question you may ask is, did it meet the warranty requirements? Now, because he had put in so much of material in the superstructure, just to lift itself, it was using up its life, not for the 1.6 tons payload. Because the system became more flexible, the life increased, the operating members' bill of quantities and the bill of materials and their weight reduced, the bearings became smaller, the hydraulic actuator became small, the reservoir had to contain less oil, the heating of the reservoir as a result of the oil being pumped is lesser, the pumping of the oil became lesser, the cycle time of operation became larger, and the warranty exceeded the 5 years. So it is a win-win situation where you are looking at design for cost when you are looking through the prism of design for life. Now, one of the most important thing is, when we are looking at all these conditions holistically, we are looking at the energy that is going through the system. Similarly, we have medical equipments, whether it is implants which is getting into our body, or it is medical devices which need to perform without failure because patient care is important and life is important. Service life is extremely important. Recently, Johnson & Johnson had a recall of implants worth $5 billion worldwide, which also included Indian patients who had received those implants. So what's the big deal about this recall? A recall of an implant necessitates removal of the previous implant from the body of the patient and introducing a new implant again. So in medical designs, factor of safety is no longer a choice forced upon by performance for design for life. At the end of the day, it is very important that these fail-safe designs come into existence. As I said earlier, pump design validation as well. When we are looking at the pump design validation, we are looking at the mean time between failures in the pump, and we are looking at how to ensure that the bearings and the seals do not fail. If the bearings and the seal fails, did the seal failure lead to the bearing failure, or did the bearing failure lead to the seal failure? It's a question of the chicken or the egg. This comes in because of the design for life calculations. And the last one is increasing the warranty, which every customer demands without a cost penalty. Again, design for life. Similarly, for mechanism validation, we are looking at whether the design will work, the transmissibility of forces, the mean time between failures, and the cost-effective designs. Now, when we are looking at all these different aspects, we need to understand that it is very important that we look at the fatigue life of the units more importantly than the factor of safety calculations. Now, let us look at some of the fatigue examples as shown in this picture. You see the crankshaft which has come down. You see the vane pump which has broken. You see one of the shafts which has gone through a fatigue failure and a bearing. In all these cases, we are looking at failures during the life of the product. Now, it is important that when we look at these kinds of warranty costly failures, we need to understand that these eat into the profitability of our organization more so than ever. When you look at any design, we are looking at fatigue means we are looking at the stress versus the number of life cycle curves factors with regard to the fatigue strength. I'm going into the technicalities a little bit over here, primarily because this is important for us to understand. It is not the factor of safety, it is the life calculations. One of the questions that people ask is, we don't have the SN curve available. There are enough methodologies available for fatigue life estimation or fatigue curve estimation based on the hardness, based on so many other factors that you can bring in and construct the SN curve even based on your failures that you have reported from the marketplace, including the material properties such as the ultimate tensile strength, the yield strength. You can come up with the endurance limit calculations. Now please understand, the stress that we are talking about here is not the stress as you find in your finite element analysis. It is the stress as you find in your finite element analysis based on amplitude of loading, which is nothing but the stress range or the stress amplitude. There is a difference between the stress at a point and the stress amplitude. It is the cyclical load stress amplitude which dictates life. If you take the case of a wheel, when you roll the sheet metal into a wheel cylinder, or for example a pressure vessel, the exterior fiber goes through tension, the internal fiber goes through compression, and when you have bent it and when you have rolled it and you have seam welded it, it is going to be in a very high state of tension, much beyond the elastic strain. Is that going to influence your fatigue life from the actual stress? No, it is going to be only the mean stress and versus that the stress amplitude. That is why I'm putting together this particular slide to enforce upon the audience that it is designed for life based on operating stresses, not based on one-of-a-kind stresses. So, when we are looking at the fatigue failures in design for life, we employ what is called as the theory of cumulative damage. The theory of cumulative damage assumes that a stress cycle with an alternating stress above the endurance limit is 10 power 7 cycles or more, 1 crore cycles or more. It inflicts a measurable permanent damage. In other words, like elephants which can remember, the object remembers those events and starts progressively coming down in performance till such time it gives up. So in other words, fatigue is the condition. Fatigue is a design, is a failure at a much less less than the design load. Fatigue is a failure at a load much less than the design load because the life has been used up. It also assumes that the total damage caused by a number of stress cycles is equal to, as stated in this picture, the summation of damages caused by the individual stresses. So, the linear damage rule or the minus rule is what we go about. So, if we have different events occurring for our product during the life cycle of the product, we decrement the life from 1 all the way till 0,
Okay.
and if the life crosses 0.5 for rotating components, and if the life crosses comes into the other side, then the object has failed. This is the condition that we look at in terms of fatigue failures over there. So the damage factor used is shown over here in this picture. It's also called as the fatigue life usage factor. Is the ratio of the consumed life towards the overall life. A damage factor of 0.35 means that 35% of the structure's life is consumed, and the failure due to the fatigue occurs when the damage factor reaches 1.0. So the assumptions and the limitations of this approach are, it does not consider the effects of the load sequence. In other words, it's a very conservative estimate. It predicts that the damage caused by the stress cycle is independent of where it occurs in the load history. It also assumes that the rate of damage accumulation is independent of the stress level. Observed behavior indicates that cracks initiate in a few cycles at high stress amplitudes, whereas almost all the life is spent on initiating the cracks at lower stress amplitudes. These are important bases. In addition to that, you give your mean stress correction if your object is going to be loaded in tensile with a tensile mean stress, or a fully reversed condition, or a compressive mean stress. For example, if you are tightening the load on the fasteners, it is a compressive mean stress, in which case you could develop fissure cracks which would not propagate, leading to an increased life. So if you were to increase the life cycle of your components without incorporating, without attracting additional costs, your assembly stresses coming as a result of the compressive stresses would help you to get more mileage for no cost at all. These are considerations that you can do at the design stage. Employ it with looking at different pros and cons, and your tightening torque will influence your fatigue life. As you look at it, lines of constant life based on the Hague diagram shown over here helps you to understand the concept of the alternating stresses. I do not want to delve too much into the theory behind it. However, the mean correction methods based on the Goodman diagram, the Gerber method, or the Soderberg method could be employed for you to increase or decrement your life cycles based on the mean correction. This is important, especially if you know for a fact from your finite element analysis that pre-stress is going to play a part. It could either decrement the life or it could be incrementing the life. Now, typically when you are looking at any particular model, the most important thing we look at is how reliable are our physical models with regard to our finite element predictions. What I am going to show you is right now a high cycle fatigue. This is a very classic case where it's a German equipment which was supplied to a petrochemical major, and the warranty period that was given over was 12 years. Components started failing after 5 years. These are, mind you, very large shafts used in the textile units for getting the polyester yarns. The tenacity in the polyester yarns come as a result of the fiber going through a heating and loading conditions wherein the crystalline orientation happens, leading to a higher tenacity on the fiber, on the polyester fiber. Now here, the Germans had done a factor of safety calculation, while what was required was a fatigue life estimation. So we were able to estimate the fatigue life, we were able to estimate the amount of life left, and the material was a utopic material. It was a very high strength 30 chronimo 8. So we were able to predict the failure to a very great amount of reliability, and the customer did not tell us as to how many cycles it failed, but we predicted 5.5 years of cycle. So this is one of the most important reliability measures that we were able to see, as a result of which customer was able to come back and say, yes, your fatigue production, your fatigue calculation is absolutely reliable. The next example is, you look at this, this was basically a strain gauging of hydraulic presses specifically for infinite life designs. The strain gauge correlation, characteristics of a pump versus the actual. These are different ways in which we can look at correlations using finite elements to establish a certain level of credibility in our analysis, as a result of which we are able to come back and say, with fit, form and function, we have been able to deliver a better performing design. The most important thing in this, in the entire aspect of this presentation, is that when we look at the calculations with regard to the design validations for warranty, it helps us to innovate our designs and give alternatives to our sales and marketing team and to our customer. It helps us to improvise upon our design for a design for life, and it helps also to indigenize our design for the warranty calculations that we need from our marketplace in this country. Improved profitability is again as a result of this approach. It gives the best to our customers and helps us to become best corporate citizens and leave a greener earth for the future generations. So this presentation helps you to understand that the fatigue life calculations through design for life enables us to ensure that we deliver on reliable designs to our customers. It has been 35 years since this process was institutionalized in the West. So it is incumbent upon us to understand that we need to have this incorporated as a part of our design process more so now, especially because of the profitability that is coming into threat in our organizations. So I invite you to provide me with questions that would help us to answer specifically with regard to your issues, or what are the answers that you are seeking from a design for life point of view to eliminate warranty issues, or to overcome warranty issues, or to provide enhanced warranty for your products. Kindly provide me with a question on the chat plane so that we will be able to answer your questions. How does design for life help us in selection of bearings? This question is a very important question. Selection of bearings is based on the static and the dynamic characteristic of bearing, the loads that are coming in from your calculations that you use in your machine data book or from your bearing supplier's manual. But the load that goes into that is going to be estimated by you as design engineer. If the load that you are going to estimate is going to be higher, necessarily you are going to use a higher service load bearing. If it is going to be lower, you are going to put a lower bearing which may fail earlier. So your prediction of your load is very important when it comes to serving the requirements of your customers in terms of mean time between failures. So it is all the more important that you look at the warranty costs. So through the prism of warranty costs, your selection of bearings. Let us say you have a set of bearings on your machine design whose bill of quantities you know. Now how are you going to ensure that you are meeting the price point of your customer while also protecting your warranty life? And you come back and your sales department comes in and says reduce the cost by 10%. How are you going to go about doing it? If you want to touch the bearing, you have to touch the load bearing structures. You have to touch the self weight of those load bearing structures, the redesign of that, the actuating load, so on and so forth, so that you have a reduced capacity bearing to influence those loads for a higher superior performance. Next question, please. In terms of reliability for on-road conditions, how are these predictions reliable? There are two different ways in which on-road life cycles can be computed. One is based on the replication of the on-road life cycles in a test track, either in your organization or at Automotive Research Association of India or any other test tracks. You go and pick up the G loading, get the events, start decrementing the life of the events of the products. Based on that, put it on a full vehicle system model, get the acceleration characteristics at every subsystem level, give those compliance statistics, transform them from a service load to an operating load to a limit load to a design for life load. And then you start looking at the warranty and see at which point of mode the failure modes are and when the replacements have to be in place during service for preventive maintenance or after service, after warranty, service after warranty. So how reliable are these? It's as reliable as your test data that comes in with regard to the accelerometers. Number one, on your torture track or on the paved paths. And it is pretty much the automotive industry has come up with a mature model for accelerated durability characteristics. So if it passes that 9 out of 10 times, it passes the real life test in the absence of material defects or manufacturing defects. So this is how vehicle manufacturers around the world, when I was working at Ford Motor Company in the US, the requirement was to bring down the product design and development cycle time from 5 years to 2 years. In other words, every 24 months a new vehicle has to be launched and the vehicle has to be reliable. So we have institutionalized this process as a part of our culture to help us to gain dividends, because service cost could kill the automotive sector because they work on thin margins. So this is a proven reliable test model that has been adopted worldwide. We encourage the Indian customers also to go through and implement the same in their own areas of activity. Any other question? If you have any questions, please send the same thing on the chat mode. It would enable us to answer the same, and also for the benefit of the other participants on the webinar. In vibrations, how can we predict fatigue life? The fatigue life computation is not dependent on whether it is a static load or a dynamic load. Different mechanisms and models are available. So you could have vibrations which are deterministic. Deterministic meaning you know the pattern of vibrations. It could be like a motor, cyclical at 3000 RPM means 50 Hertz. You are having the forcing frequencies. Or it could be an engine, could be a generator set, it could be a pump, it could be a reciprocating pump, it could be a jet pump, it could be a centrifugal pump. These are all called as deterministic loads. Random vibrations which occur like earthquake loads or loads as a result of going on the track or the road, these are called as probabilistic models. Both are available in softwares today to adapt you to decrement the loading, to decrement the life based on loading, to help you to achieve the desirable life characteristics and look at where the failure modes would occur. So both deterministic and non-deterministic approach can be applied with a reliable amount of accuracy. When I say reliable amount of accuracy, this method is conservative. In other words, it will give you the minimum life expectancy. In other words, you are assured of a life beyond that minimum, and it has nothing to do with factor of safety. Interestingly, when you talk about dynamics, the worst kinds of dynamics that you would ever face is probably in a piston inside an engine, where explosions are coming in, where the piston is facing the explosions inside the engine. They are nothing but detonations every cycle. 4-stroke means every 2 cycle, 2-stroke means every cycle, right? Now, when you are looking at this condition, what kind of factor of safety would you have? Typically, factor of safety for a piston is 0.8. It is not even 1. But how does the piston live? Piston lives for the entire duration of the vehicle. If the design is going to be made on account of factor of safety, it's not going to live. But if it's done based on design for life, it lives to tell the story. So this is very important. This is a very classic example where we need to stop in terms of conventional design practices in terms of factor of safety. Factor of safety is a feel-good factor for the design engineer, not for the product. So if you want a feel-good factor for the product, it is designed for life. Are there any other questions? If there are no further questions, you can always contact us on info@egs.co.in. We have been helping customers to deliver on their design requirements and their product requirements. One of the questions that is coming here is SolidWorks a single point solution to address all the issues discussed here? Whatever presentation I have shown you over here are by customers as well as by us using SolidWorks and its products such as SolidWorks Simulation, SolidWorks Flow Simulation, SolidWorks Simulation Premium. In all these things you have the fatigue module, which helps you to understand and assess the warranty life. So when we implement the SolidWorks suite of products in any customers, we look at their challenges in terms of three things: cost, time, and quality that the customer is seeking. Our alignment towards these three things, we take it upon ourselves, provide an implementation plan with the software so that inside an integrated design environment, a person who's not so well versed with finite elements is still able to get a reliable calculation based on a process. The implementation of this is more so to do with the process, establishing a process in design which would empower you to develop reliable design so that you can tell with confidence, it is not my life which is a problem, it is something else in the product. So yes, this is a single stop solution where you can use SolidWorks with all these add-on integrated products sitting inside, which provides you with this and enables you as a customer to address your quality issues, cost issues, and time issues with regard to product design and development. Any other question? Well, we thank you for this time and patience. We apologize for the delay that we started 5 minutes late earlier this morning. We welcome any question that you may have with regard to your issues for your products. We would love to hear from you to try and address and solve the same. Our interest lies in solving your problem issues so that they go away as one of our favored customers. We thank you for taking this time. We invite you to send us the queries at info@egs.co.in or contact one of our 3 offices in Chennai, Coimbatore or Trichy, and we would be happy to address your queries. Thank you and have a good day.